As we have said, the main goal of the transport layer is to bring messages from a process of one host to the process of another. You remember that a host at the network level is defined by the IP. If we talk about the Children Houses example, the host is the house, and every child is a process. If you look at the image before you, there are 4 processes running on 3 hosts. On the leftmost host, we run a P3 process. On the central host, we run 2 processes, P1 and P2. And on the 4th host, we run process P4. You can see that the whole process is connected through a socket, which is a combination of an IP address common for the whole host and a port that is unique for each process. As we can see here is that process P3 tries to connect to process P1, and let's say process P4 with P2. So how do we know how to demultiplex this message to the right process if 2 messages arrive at the central point? Let's try to understand how it happens. So how does message demultiplexing work? The host receives an IP datagram, which is a message on the network layer level. Every datagram contains the IP of the sender, the sending host address, and the IP address of the host that the datagram should arrive at, the receiver. Every datagram contains a transportation layer segment, and every segment contains its source and destination ports. So with the destination IP address, it is possible to reach a specific host, and then through the ports to do the demultiplexing. We'll now look in more detail at how it happens in the case of TCP and UDP. In the case of UDP, the protocol doesn't need to open a connection before we send data. This method is called connectionless. Let's try to understand how message demultiplexing works in this case. First of all, we need to open the socket out of the process. In our example, we will open a datagram socket as it's used within the UDP protocol. This socket will listen to port 12534, which we have chosen randomly. When we created the datagram on the client side and want to send it to the UDP socket, we'll need to define the destination IP to reach the host at the other end. And afterward, the destination port, which will say to which process the datagram belongs, because we said every process listens to a specific port. The interesting question here is what will happen to 2 messages which have the same destination IP, the same destination port number, but different source IPs. That is, they came from different hosts. In a datagram socket or UDP, the 2 messages will simply be sent to the same socket and get to the same process. Let's see a specific example of a connectionless UDP case. So we have here 3 processes. Process P3, located in one host, listening to port 9157. Process P1, listening to port 6428. And process P4, listening to port 5775. If now process P4 sends a message to process P1, what should the source port and the destination port be? As we said, the source port should be the same as the port the message left from, meaning the source will be port 5775, and the destination port will be equal to the port number P1 listens to, 6428 in our case. The IP address will be the IP of the host running process P4, and the destination IP will be the host running process P1. So if now 2 messages arrive to process P1 from different processes P3 and P4, the destination port and the destination IP are the same. Both of the messages will arrive to the same process. Note that this will happen in case we are using connectionless protocols, UDP. In the case of connection-oriented TCP protocol, these things differ, and now we will see why. Let's see how message demultiplexing is implemented in TCP. Now, in the case of TCP, the socket will be defined by the quartet: source IP, source port, destination IP, destination port. You see that, unlike the datagram socket, we have two values added: source IP and source port. Now, to do demultiplexing right, we will use all four values. The same server can support several TCP sockets, and every socket, as we said, is defined by the quartet. For example, web servers have different sockets for each client trying to reach them. And in the case of non-persistent HTTP, there will be a separate socket open for each request. Let's see an example of TCP connection-oriented demultiplexing. Unlike with UDP socket, we need to describe every connection between two processes. We'll use the quartet of source IP, source port, destination IP, and destination port. Let's look at an example with three hosts. The left host has an IP A, the central host has IP B, and the right host has IP C. The left-hand host runs process P1. The central runs three processes: P4, P5, P6. And the right hand, two processes, P2 and P3. Now, let's say both hosts, left and right, running processes P1, P2, and P3, are trying to send messages to processes P4, P5, and P6. In this specific case, all these messages will have destination port 80. The destination IP will be destination IPB. But still, because we need to describe every connection separately, here is the case where the source IP and the source port start playing a part. In the case of the quartet, they identify every connection. So it will be obvious that P2 is really talking to P6, P3 is talking to P5, and P1 to P4. In contrast to UDP, where we used a datagram socket. And the destination IP was the same, and the destination port was the same. All segments reach the same process. Here, we have to describe the connection with more data, and because of that, we use the whole quartet. Furthermore, the process can listen to several sockets. We can say that every thread in that process will listen to a different socket. This is exactly what you see now. The example here has process P4. In contrast to the previous case where we had several processes on the central host, we have a single process, P4, which is listening to several sockets, each in a separate thread of the process. Still, we know how to identify every socket used by each thread because we describe the appropriate connections by the quartet. And we know how to get the right thread in the process.